Hello, and welcome to another session on flames in Cantera. Today, we will start off from where we left off in the previous session. Um, in the previous class, we saw how to initialize a flame object. And what does Cantera do internally whenever we initialize it? Today, we will look at how to solve the initial grid that we set up and what kind of outputs does Cantera provide. So let's start on that. So if you remember from the previous class, what we did was to assign a grid and assign a phase, a gas phase to the grid. We saw the internal grid structure and the different plots of temperature, velocity, density, and so on. To solve all these equations, there are two commands that you will have to know. One is called set refine criteria, and the second is called solve. That's very intuitive, actually. So let's look at let's look at the refining criteria. So let's look at the help f dot set refine criteria. Okay, so what happens is with set refine criteria, you can actually tell Cantera how to refine these grid points as the simulation progresses. So there are a couple of inputs that you can provide. One is the ratio, slope, curve, prune. I personally only use ratio, slope, and curve, and I will give you some default values for it as well that I typically like for my flame simulations. So ratio is just the ratio of values of adjacent points. If there are 2 points, Cantera just looks at the ratio of values that it has. And if it exceeds the ratio, then it will refine the point, add more grid points over there. Now, the second one is slope. And this, again, it just takes the value difference, rather. So it takes the value of 2 adjacent points. If, again, the value is greater than a certain threshold, it will add more grid points there. And the final one that I use is called curve. Here, instead of value, Cantera looks at the gradient itself of how the slope is changing. And if the slope is, again, greater than a certain magnitude that you've specified, more grid points are added. So typically, in my simulations, what I do is I define f dot, or let me just use the up arrow. I define the ratio as 3, and then I define the slope. I define the slope as 0.06. And finally, I define the curve as 0.12. So these are values that I've seen in my experience work well for me for the typical flame simulations that I do in Cantera. So we'll just hit the enter key, and now the refinement criteria is set for Cantera. Next command is solve. So let's look at the help for solve. All right, so here again, you have certain inputs that you can provide. The log level, refine grid, and auto. Log level is, you can define the amount of information that Cantera gives you while the simulation is going on. So a log level of 0 is that there'll be complete silence. So Cantera will start to solve the equations, and it'll finally generate the output when it's ready. So subsequently, there is level 1, 2, 3, up to 5. 5 is the most verbose. So Cantera will define it, or rather produce output at each and every level, everything that it is doing internally. Generally, I find that to be too much information. So I keep log level as 1, and we will see what that does. Then the second input is refine grid, which is either true or false, which is if you say refine grid as true, then Cantera will proceed with automatic grid refinement, otherwise not. And then finally is auto equals false or true. Auto, if you say auto as true, then Cantera, if there are any, when the simulation is going on, if Cantera encounters any errors, it tries to recover from the errors and takes a step back, maybe takes a smaller time step or does something to calculate do the calculations again, so as to avoid those errors that occurred. So generally, I just keep auto as true. So let's actually use this command now, f.solve, and we will say log level equals 1. Then we will say refine grid equals true, and auto equals true as well. Okay, now when we hit the enter key, then Cantera will start to solve these equations on each of these grid points, and you will see some outputs as well. Okay, so here it is trying to solve these equations. It is encountering some failures and some successes. So it is trying to adjust its calculations so that the whole thing goes through. So let's wait. It'll probably take another couple of minutes. All right. So what it does is, see, it says problem solved on 201 grid points. If you remember, we only started with a couple of grid points, and we can go and see what did it look like. The grid initially was 1, 2, 3, 4, 5, 6, 7, 8, just 8 grid points, including the start and the end point. Now, at the end of the solution, you have 201 grid points. So that means that Cantera has actually gone in and refined the grid. And you can also see that. So now if we write f.grid, you see so many numbers pop up. These are the coordinates of each of these grid points. And as we've done in the past, we will, let's look at some of these outputs. So let's look at velocity, for example, and that is where we started. So plt.plot f.grid, comma, f.velocity. Okay, so now you see things have changed. Initially, everything was flatlined. So if you go back in history and see, this was the temperature, this was the velocity. Velocity was 0 on each of the grid points. Now, if you see, there is a certain amount of velocity, that is the incoming velocity for the mixture. And as soon as the gases expand due to combustion, you see a raise in velocity. And then finally, these are the burn products. So similarly, let's look at temperature. So we say f.t. And again, see, it starts with some 300 Kelvin, I suppose that was the initial temperature. And then the temperature spikes and then goes stable. So this is what you will see everywhere. There is one important function that that gives you a very good idea of the reactions themselves, and that's known as heat release rate. So let's do that. F.heat release rate. So now if you see that there is a sharp spike and then everything goes down. So what this shows is that this exact location, this exact point is the location of the flame front. This is where all the reactions are happening. The heat is being released, and the heat release is in watts per meter cube. So this 6 into 10 power 9 is the watts per meter cube of heat that was generated at this particular point. And so as soon as the reactions happen, the heat goes up, and then it finally comes down when the reactions stop. Now let's do one more thing. Let's stop grid refinement altogether. All right. So before doing that, let's quickly plot the velocity again. Velocity. Okay, so this is the velocity right now. Now what I will do is I will go back to the command set refinement, and I will switch some things off, or rather sorry, I will go to the command f.solve and switch the grid refinement. So now I will say, we have to initialize it, by the way, again. So because we should have, if we should have saved the initial composition of the incoming mixture, but let's do that again. So it will be gas dot, sorry, okay, gas dot TP equals 300 CT dot 1 atmosphere, and then CT, sorry, and then gas, sorry, we will have to set the composition again as well. And so gas dot set equivalence ratio, and to do an apples to apples comparison, I want to set the same equivalence ratio that we had in the beginning. So I think that was equivalence ratio of 1, and the fuel is C2H6, and oxidizer is O2. Okay, all right. So now the function is already there. So let me actually reinitialize the flame as well. F equals CT dot free flame gas, comma, width equals width. So this will initialize the grid once more, right? And let me use the up arrow. It's becoming a bit tedious. Let me refine the set refinement criteria to the same thing that we originally had. And then finally, we will use the solve command. It's the same thing that we originally had again. So f.solve. Now, what I will do is, instead of true, I will put the grid refinement to false. So we still have the same grid refinement criteria set that we originally had, but now it has been set to false in the solve command. So let's see what that does. Okay, so now this was a really, really short simulation. And if you see, it says problem solved on 9 grid points. It has not refined the grid at all. And now if we go and check the velocity of in the solution, and you say plot, again, let me use the up arrow so that I don't have to type the whole thing again. Now, if we say f dot velocity, it's so it is so discontinuous, or rather, it has so many corners and edges. So that's what happens when you disable the grid refinement. This was with grid refinement. This is without grid refinement. So, I mean, you get a ballpark. You get a general area where the reaction is happening, but certainly not enough information if you really want to dive into the simulation, into the solution. So I would highly recommend that you keep the refinement criteria on at all times whenever you are solving flame equations on Cantera. And that should, the default values that I provided, the ones that I like for set refinement criteria, I've seen them to work pretty well in most gas compositions. Sometimes with, say, hydrogen, things can change because hydrogen has a very high flame velocity and very fast reaction rates. So if you see the solution to be not very smooth with any particular fuel mixture, then you can again refine or rather change the refinement criteria. One last thing that I would like to mention is that you can also find the flame velocity, or the flame speed rather, the flame speed using this simulation. All you have to do is just find the flame velocity at the first or the inlet point. So I will say f dot velocity 0, 0.08 meters per second, that is 80 millimeters or 8 centimeters per second. Now again, this is not a this is not a very good number, because as you can see, the solution is very rough. And so once you refine the criteria, you'll get a certain different number. But this number represents the flame speed of this particular gas or this particular fuel and air mixture, because that is the definition, right? The flame velocity is where the incoming mixture and the combustion, they kind of balance each other out. So the velocity with which you have to push the mixture in is the flame velocity, and that is what we've done here. All right, so that was it. And in the next lecture, we will look at some other type of flames that Cantera can solve. So okay, that was the end of this lecture. Thank you.